Okay, so we are recording. Here's where we left off last time. We were talking about parameterizations, and we were last time taking given parameterizations and trying to figure out what is the underlying curve that it describes. So here we're going to go in the opposite order. Here we're going to say there's an underlying curve for which I want to create a parameterization. And this is called parametrizing the curve. Okay, all right. So I'm going to show you, again, it's a tools for your toolbox kind of a situation. There is not a single, always this approach for how to parameterize curves. I'm going to start with my favorite one. This is my desert island parameterization method. And it does have a shortcoming. It only works for graphs. It only works, in other words, if your curve has an equation in which one of the variables is explicitly given as a function of the other. Now, we're going to say more about this term here, by the way, graph, a little bit later on. It is a term that does tend to get abused more than it should. Anyway, we'll come back to that later time. For the moment, all you need to know about a graph is that it means one of the variables is an explicit function of the other. And here's the trick. The awesome trick. If you have a graph, whatever is your input variable, just let that be your parameter. It's that easy. Whatever is the input variable, make that the parameter. Let me show you an example. So, okay, notice, we have here a graph. Now, I know specifically that this is a graph, right? Because we have y equals, and then it's an explicit function of x. So let's follow the rule. The rule says whatever the input variable is, let's let that be our parameter. Okay, my input variable is x, so I'm going to let x equal to t. And I claim it's all over but the shouting. Now, we do have to kind of think through what y is, but we don't have any choice in the matter anymore, I claim, because notice that if x is t, then unavoidably y has to be t squared. And we're done. Check it out. We have ourselves a parameterization. This is a parameterization because we have position as a function of time. Isn't that nice? Right? It's an easy trick to remember. It's very powerful in the sense that it works for any graph. And not every curve is a graph. Okay, fine, that's disappointing. But many curves are graphs. And in that case, it's just bam, simple. Right? Okay, so my favorite method, yes.
So what happens if, in this case, like maybe we did like y equals t, and then we said like,
that'd be a tragic miscue, right? Yeah. Don't do that.
Like, what happens if you have like the square root problem where
Don't do that. Just don't do that. No, the graph parameterization trick is you've got to follow the instructions. And if you get off of the trail, right, okay, now you're on your own, and I just don't, so no comment. I mean, I'm all for trying different things, right? But the point to this is whatever the input variable is, let that be the parameter, and exactly so that you will avoid problems like you described. Yeah, exactly. Does that make sense?
Yeah.
Okay, yeah. Okie dokie. So let's see another example of this. Now you look at this equation right here, and there's two problems with this equation. For one thing, I do not have, as currently written, one variable as a function of the others. Okay, so it's not written as a graph. Worse, I cannot solve for y because this equation is transcendental in y. Right? So I can't solve for y as a function of x. Seems discouraging, but then you notice it actually is pretty easy to solve for x as a function of y. There's no law that says that y has to be the output and x has to be the input. There's no magic mathematical significance to alphabetical order, right? So if you can make any variable an explicit function of the other, same trick works. So notice I've solved for x, so I have x as a function of y. That means that y is my input variable. I'm going to follow the rule. Let the input variable y be my parameter. And in so doing, with y equal to t, that forces x to be all that jazz right there. Everybody good? Okay. All righty. Okay. Now, again, sorry. Yeah. Yep.
So when doing parameterization, is one of the variables always going to equal just t?
For the graph parameterization as I've shown it to you here, yes.
Okay.
But that is not for every parameterization. There's plenty of parameterizations that are just they're just different, right? So this is just, again, one tool of many, and in this case, yes, but in other cases, no. Okay. All right. Okay, now here's another tool that can be useful in different circumstances, and that is what I'm going to loosely call vector algebra. Vectors are really handy in a lot of ways. Of course, you know this from linear algebra. But here's the scenario. Suppose you have a wheel, and I like to think of a bicycle wheel, and it's rolling. Right, so off it goes to the right there, and it's rolling on top of the x-axis, just to so we have a reference point there. Okay, and on this wheel we have a reflector. Again, going with the bicycle wheel analogy, here's the reflector on the edge of the wheel. And now you can imagine geometrically, or you can think back to any time that you've seen a bicycle riding on the road under a street lamp at night, right? And you see that the reflector makes this weird kind of pattern as it passes you, right? And so in particular, that reflector is going to start going up because the wheel is sort of rotating, clockwise, and that makes the reflector go up, but it also goes to the right because of the movement of the wheel, and it's kind of like that. And then over a longer distance, it would do some, kind of like that. Does that look familiar to everybody? Okay. All right. So how do we parameterize that curve? Well, gosh, it turns out it's practically impossible to solve for y as a function of x. I mean, it's not that it can't be done, but it's you don't want to try to do that. That's bad. It's really hard. So we're going to take a totally different approach. We're not going to use the graph parameterization. I'm going to make the following observation, and that is the point describing where the reflector is at a given moment. And by the way, you'll notice over here I have a moment described that here's where my wheel is. It's rotated, it's rolled down the road a certain distance there. When it has rolled down that amount, the reflector has rotated around the wheel a certain amount. And so we're at that point. Notice, though, that this reflector location is the sum of the location of the axle and let's see, I'll do this in purple, sure. And this, what I'm going to call difference vector there. All right, so orange is equal to blue plus purple. All right. Now, why is this useful? It turns out that very often, and this is a great example of the following scenario, sometimes a vector can be written as a sum of simpler to understand vectors, where the whole is not the sum of the parts. The difficulty is not accumulating, you might say. The difficulty in understanding the orange vector by itself is tremendous. The blue vector is actually pretty easy. The purple vector is actually not that bad also. So we're going to look at the blue and the purple, and then we're just going to add them up. That'll give us our otherwise hard to understand orange. All right. So let's take them one at a time. We'll start with the blue vector. What can I say about the blue vector? The first thing I'll observe is, and let me rewrite this as a point for sort of geometric convenience. That point is always at the same height. It's the axle of the bicycle, right? Round wheels and all that. You personally don't bounce up and down as you roll down the road. So your y coordinate is always just whatever the radius of that wheel is. Everybody happy with that? Okay. All right. Now, next thing I'm going to observe, and this is a little tricky. This is a key insight. this is just about the way wheels roll. Let's see here, colors. Okay, so the amount of rubber that has touched road has to equal to the amount of road that has touched rubber. Does that make sense to everybody? It's just a purely physical appeal. But if that wasn't true, you'd be either skidding along or you'd be burning rubber. Your wheel was slipping because you're pushing too hard or something. So we're going to assume dry, flat road, and you're not, doing anything crazy. Then this is just how rolling works. Everybody buy it? Okay. All right. So the good news is, if you think about it, this is what we're interested in, the x-coordinate. The amount of road that has touched rubber is the x-coordinate that we're interested in. The amount of rubber that has touched road is something that I can get my hands on a little bit more easily. And specifically, what I'm going to do is I'm going to define, I eventually need to create a parameter to tell me how much, time has passed or, some sort of a parameter to write things in terms of, and I'm going to use this angle. Oh, if I can write better. This angle here. So by what angle, we use radians, of course. By what angle has the wheel rotated? Okay, so I'm going to call that t. Again, you can think of that as being time. And then the question of how fast are you riding the bicycle comes up. Let's not worry about that. So you can loosely think of it as time, but in fact, it's just a parameter. It's a foot in the door that I'm going to write everything in terms of. Okay, so we've got that t. So old high school geometry formula tells us that let's see here, colors again. That the amount of the length here of this arc, in other words, the amount of rubber that has touched road, namely the amount of road that has touched rubber, namely the x-coordinate that I'm looking for, right? That arc length is just radius times angle. Everybody's happy? Okay. All right. So a little bit of clever reasoning, but otherwise it's just kind of a matter of writing it down. Okay. All right. Now let's talk about this difference vector. So completely independent of the axle's location, we're going to talk about that vector right there. Now recall, and I'm going to think of this vector, by the way, as a vector. Vectors do not have a location, right? Vectors have a direction and a magnitude. They do not have a location. And so I can draw that vector wherever I want, and I'm going to find it more convenient to redraw that vector so that its tail is at the origin, because then as the wheel rotates, it just kind of goes around in a circle centered at the origin, which is easy to describe. Right? And having done that, no problem. This vector that I'm interested in here, I can write that using polar coordinates. I can write that in terms of this angle theta as a cosine theta, a sine theta. Just a little bit of trig there. Everybody comfortable with that? All right. Now, problem. I need to add this to the axle vector up there. Axle is written in terms of t. This d vector is written in terms of theta. Those are not the same parameter. I need everything written in terms of a single parameter. So what I'm going to have to do now is make the observation that these parameters are actually related. And let's see, what color did I use for I think I used purple? No. Well, anyway, it doesn't. I'm going to use blue. So the angle t from before and the angle theta, they always add up to 3 pi over 2. Now again, another geometric appeal. You look at how those angles are defined, and as the thing moves, well, t gets larger, theta gets smaller, but in total they add up to 3 pi over 2. Is that cool? So t is increasing, theta is decreasing. Okay, well, if they add up to 3 pi over 2, then I can just solve for theta, right? This angle theta that I had written, that I had written things in terms of over there. It's just 3 pi over 2 minus t, and a little bit of trig, flashbacks to high school trig, turns that into that. Now, I know that a lot of y'all are like, oh my gosh, I don't remember how that works. Trig was a long time ago, what have you. I want to remind y'all specifically that what happened there is I used the angle addition formulas. So these are standard formulas of trig, cosine of a plus b, and sine of a plus b. These are formulas that everybody should know. I know that high school trig teachers seem to have decided, I don't know what the basis of the decision was, but they seem to have decided that students don't need to know these formulas anymore. That's really not true. Certainly for this class, certainly for anyone who's going to do anything in engineering or physics, angle addition formulas come up all the time. So I'm going to insist everybody needs to know the angle addition formulas. Just for sine and cosine, don't bother with the trig formula or the cosecant formula. Just sine and cosine is plenty good enough. But you do need to know those formulas. And that's what allows us to do that conversion right there. All right? Is that cool? Okay, so please make sure you know those formulas, and then once you do, then you can apply those formulas to do that transition. And it's all over but the shouting. Let's see here. We recall that the big idea here was that the point I'm interested in, I can get this all here on the page. Oh, no, wrong color. This point that I'm interested in is equal to, it was equal to the A vector, which we solved for there, plus this D vector. Oh, whoops, missed. Try that again. Which we solved for there, and boom, we're done. We have location of the reflector as a great big function of t. We have parameterized that wacky curve. It's not conveniently represented as a graph. Graph parameterization method would have been a nightmare. Using vector addition, a little bit of geometry, a little bit of trig, not that bad. Everybody happy? Okay. Okie dokie. So here's another example. This is another sort of use vectors kind of a thing. Suppose you want to parameterize a line. How are we going to parameterize a line? Now, I emphasize not what is the equation of a line, right? But how do I get position on the line as a function of, again, let's call it time, right? Some parameter where I get, x comma y equals, and then a function of t. So what we're going to do here is, and you may have seen this, you probably have seen this back in Math218, but anyway, let's do it anyway. The big idea is if I start with some point x naught that is on the line, and if I have some vector v that is parallel to the line, notice that every other point on the line, every one of them, is going to be your x naught plus some multiple of your v vector. And that little innocent observation gives you a parameterization. That tells you that, you can describe, again, every point in the process, as you trace out that line, x and y, namely what I call the x vector, is that formula, which is a function of just t. Everybody happy? Okay. Right. Okay, here's another one. This is another really good trick. Sometimes you want to parameterize something that's that's not that different from something you've already parameterized. And then you find yourself thinking, am I going to have to reinvent the wheel here? I already went to a bunch of trouble and parameterized something that's so similar to, surely I can take what I've already got, just tweak it appropriately, right? So I call this deforming an existing parameterization. So here we go. Suppose you want to parameterize this ellipse. Specifically ellipse with this equation. Now think back to high school trig, and you know that, let's see here, because of this 3 here, I said trig, I meant algebra, but because of that 3, the x radius of this ellipse is 3, and then likewise because of this 2, right here, you know sort of the y radius is that 2. So there's our ellipse, and we think to ourselves, well, it's not a circle, but I know that this is a lot like a circle. In fact, it's just a deformation of a circle. It's a circle that I've tweaked. So let's talk about the circle. Here's the circle, unit circle, which again we have already parameterized. We already know cosine t comma sine t does the unit circle. Now, so there's a parameterization I have, there's a parameterization I want, and I can see exactly what I need to do to turn the one into the other. What I need to do, apparently, is I need to stretch in the x direction by a factor of 3, and then I need to stretch in the y direction by a factor of 2. Okay, so again, parameterization I have, parameterization I want, and I see exactly what I need to do to turn the one into the other. And so, roughly speaking, go ahead. Here's that goes. Notice I'm going to start here with cosine t sine t. That parameterizes my original, well, my existing parametric curve C. And then, okay, I want to stretch by a factor of 3 in the x direction? Sure. Boom. Just multiply all those x coordinates by 3. That literally stretches by a factor of 3 in the x direction. And I want to stretch by a factor of 2 in the y direction. Okay, so multiply by 2 on the y coordinate. And that does the deformation needed, and thus gives me my stretched out unit circle, aka my ellipse. What do you think? Anybody see the idea there? Always going to be a little different, right? It won't always be that you're starting with a circle. It won't always be that you're stretching. You might be shifting, right? Or it might be a combination. You might be stretching and then shifting, what have you, right? But the main idea is to take a parameterization you have, identify what needs to be done to it to get the thing you want to parameterize, and then go ahead. Okay. All right. Okay, so now let's take a quick pause on the examples. Let me stand back perspective. What is a parameterization? What is an equation? How are they different? A lot of people will point out, and I guess technically this is true, that a parameterization is kind of an equation. Because here's a parameterization, and look, there's an equal sign, right? So it's kind of an equation in a way. But I'm going to call that a kind of a quibble. Here's the important distinction, the unavoidable distinction between what I think should be called a parameterization and what I think should be called an equation. A parameterization is a point generator. It's a little factory where you can put in any value, any number t, doesn't matter, any number t, and what comes out is a point on your curve. So we're literally making points when we have a parameterization. Does that make sense to everybody? Okay. I emphasize that is not what an equation is, right? Classically, when we write an equation in the usual sense, an equation is what I call a point tester. So, x plus y equals 5 is an equation. And the thing is, what you put into that is a point that you don't know if it's on the curve or not, right? You can take any equation, x plus y equals 5, you can plug in whatever point you want, and the equation tests, and the equation either works, in which case, yes, that point you just plugged in is on the curve, or it doesn't work, in which case, no, that point you plugged in is not on the curve. Right? But an equation doesn't create or generate points. It's a way to test points. It does not create points. Everybody see the difference there? Okay. So, all right. So with that idea in mind, and I just think it's important to see the important distinction. But this gives me a strategy for how to answer this question, which is, okay, here's a, let me do it like this. Here is a parametric curve. Three-dimensional parametric curve, right? X, Y, and Z, functions of t. And I want to know, where does that intersect this plane described by this equation? How would I find that intersection? And, well, the big plan is to take the points that I'm generating. Here's how I generate points. All right, you plug into the parameterization any value of t, you plug in, out comes a point that's definitely on the curve, and then I'm going to test them by way of the equation. I'm going to test to see if they are also on the plane. And if they are also on the plane, then, well, I've got points that were created to be on the curve, and they've tested to also be on the plane, and therefore they are on the intersection of the point of the curve and the plane. Strategically, does that make sense? Everybody happy? Alrighty. So yeah, this is a matter of doing it. The parameterization, again, pretty straightforward. Don't forget that when you have a parameterization, that's telling you x, y, and z as functions of t. All right, that's where these equations came from that define the parameterization. And then let's see here, the testing. To do the test, the x, I've got to plug that in for where the x is in the test. Namely, that's got to turn into t squared minus 1. And then let's see the y. Well, that goes where the y is in the test, which means that y becomes t plus 1. And then let's see, I'll use blue. Z goes there, which goes there. And so all together, my big test of the parameterized points gives me this equation. This is the equation I need to be true in order for everything to work. And that's just a little bit of algebra, multiply out, collect terms, cancellation, blah, blah. And you end up with this, which is easily solved to give you this. And that's the value of t. Now, we're not quite done, but it's all over except for the last little step here. That has told us the value of t that generates the points that test positively, right? So to get those points, okay, well then, yeah, you have to plug into the parameterization to get the actual points. Everybody see the process there? Nice little trick. We're capitalizing, I emphasize, the whole strategy for this exercise comes out of thinking about fundamentally what parameterizations do, what equations do, and specifically how those are different. Okay. All right. Moving along. So let's talk about lines in space for a second. Lines in space, we parameterize. We've already talked about how to parameterize a line, no problem. You need a point on the line. You need a vector parallel to the line, and then formula from 2 pages back. Okay. But what if you want an equation for a line in space? Question.
What does the symbol to the left of the line equation?
Great question. I'll get to that when I get to that part of the thing. Yeah, totally. Okay, so we know how to parameterize a line in space, but if I want an equation, aka if I want a point tester, because that's what equations do, right? How would I test points for either yes or no being on the line? if it's a line in space. So here's the big idea. I know my parameterization is going to look something like that, assuming, of course, that this is the point on the line and this is the vector parallel to the line. So the very first test I'm going to write down is a poor test. It's a smart alecky test, but it's a foot in the door, and so bear with me. And so, yeah, to your question, what this says is the test. If you come at me with X, Y, Z, and you want to know, is that point on the line, I'm going to ask, does there exist? I'll write this over here. There exists, or there is, does there exist some value of t such that, this is just a little math shorthand, math slang. Does there exist some value of t so that the parameterization generates it? Now, this is a bad test. If somebody comes at you with an X, Y, Z and says, hey, is there some value of t that generates this X, Y, Z? What are you supposed to do with that? Are you supposed to sit there and start trial and error, just plugging in values of t with your fingers crossed and hoping that it... No, right? That's a terrible test. Okay. But what you can do, a clever move, is to say, well, look, if there is a value of t that makes this vector equation work, it would then likewise have to make all of the coordinate equations work. In other words, the value of t I'm looking for would have to give me the correct x coordinate as x naught plus t times a. And I can tell you exactly what the necessary value of t is to make that first coordinate equation work. T would have to be this. Now, simultaneously, I would also need that value of t to give me the right y coordinate as y naught plus t times b. And I can tell you what that value of t would have to be. It would have to be this to make that second coordinate equation work. And likewise, to make the third coordinate equation work, you would need t to equal to that. So looking at one coordinate at a time, the ridiculous test, hey, is there a value of t that generates the point in question, turns into, is there a value of t, color choices, is there a value of t that is simultaneously equal to all three of these things? And now I make a strategic observation. This question, is there a value of t that's simultaneously equal to all three of these things? Well, that's true if and only if those three things are all equal to each other. Right? I mean, is there a value of t that's equal to 3 and 3 and 5? No, that's stupid, right? Of course not. No. Is there a value of t that's equal to 4 and 4 and 4? Yeah, of course it's 4, right? I mean, it's so obvious. It sounds hard when you say it because it's so obviously true, right? So what's beautiful about this argument is that it has done the job that we needed it to do. We have now turned a bad test. Let's see, I'll do this one in red because we don't like it. We've turned a bad test into a good test because this test down here is easy. I can just compute all three of these things and just look and see if they're the same. If they're all the same, cool, we win. Game over. Okay. All right. So just FYI, these equations here are called the symmetric equations. This is your point tester for a line in space. It's basically, it serves the role that an equation does for a curve in the XY plane. It's a point tester. Yep.
Does it only work for a line?
Yeah, this argument here, yeah, specifically, you'll notice that the whole thing starts with this parameterization, which is specifically a line. Yeah, right. Okay, so neat move. Nice little trick. Okay, moving on to dot products. Good news. Y'all already know dot products. So this is another one I'm going to be really, really, really terse on because y'all already know all the fundamental facts of dot products from Math219. So I'm just going to say review, make sure you're good with all that, and we're basically good. I have a couple of, I'm going to call them kind of cultural observations about dot products. I think it's nice to observe that dot products are the model, they're the motivating example of inner products. And recall, inner products, a very sophisticated idea from linear algebra, right? A very powerful idea, right? I don't know what examples your instructors may have shown you, but ultimately, Fourier series are a result of a very cleverly chosen inner product, and are easy to work out. You know, these seemingly magic formulas of, Fourier coefficients. That's just a matter of using inner products in just the right way. And in case you might be more persuaded by this next example, turns out some of the original ideas in image compression ultimately come from a arguably even more clever inner product. So anyway, big deal inner products, and it all comes out of dot products. So dot products are really important. Okay, now I have a personal pet peeve. I don't know what you'd call it, but anyway, it's a language thing, but again, kind of a cultural point. So our book and many others use these two words interchangeably. I don't care for this. I think it's a mistake. I think it's opportunity missed at best. So let me explain why I have a problem with that. There's a couple of different ideas that might pop into your head when you see these words. Now, the first idea is what I'm going to call a geometric idea. And by a geometric idea, I mean we're talking about if you have one direction and another direction, and if the angle between those two directions is pi over 2, 90 degrees. Right? So that's an intrinsically geometric idea because it's about directions and angles. Intrinsically geometric. Very importantly, only non-zero vectors actually define directions. You can't ask me what direction does the zero vector point. It doesn't point. It has no length with which to point. Right? Does that make sense? Okay. So the geometric idea, whatever we're going to call it, the geometric idea that this relates to can only apply to non-zero vectors. Now, here's another idea that again you'll conjure in your mind when you see this, and that is what I'm going to call an algebraic idea, a purely algebraic idea, and it's dot product equals 0, right? We know that's got something to do with these words, and that dot product equals 0 makes perfect sense, whether the vectors are 0 or not 0, or who cares, whatever. If the dot product's 0, cool. Okay, so these are importantly different ideas. So I like to make the observation we have two distinct but closely related concepts. We have two distinct words. It's perfect. We should pair them up. We should have one to mean one idea and one word to mean the other idea. And we shouldn't be blurring them and conflating them because, my gosh, they're distinct ideas. They're importantly different ideas. Right? So my move on this is to use perpendicular. Colors. Perpendicular to mean the geometric idea. So when you say the word perpendicular, you better make sure that none of those vectors can be the zero vector. Zero is not perpendicular to anything. It doesn't have a direction with which to be perpendicular. And then I like to, therefore, process of elimination, use orthogonal to mean the algebraic idea, namely to mean that dot product is equal to 0. Okay, so I think this is important. Now, I did not get this finicky until long after I had seen these ideas in high school, etc. And so I, got brought up with some bad habits, and you might likely catch me breaking my own rule somewhere along in here and say perpendicular when I mean orthogonal or vice versa. And so I'm just going to apologize in advance for, when I do that. Probably it's bound to happen, right? But I would love for y'all to correct me on that, right? It allows my mistakes to be a good example for everybody else. And I'm going to do my best, and I'm going to ask that y'all do your best as well. Yes?
So can I say the zero vector is orthogonal to all vectors?
Yes, the zero vector is orthogonal to all vectors. Because, yeah, exactly. Dot product equals 0 is just going to happen. So, yeah, totally. Oh. Exactly. All right. Okay, so a couple other things I want to talk about related to dot products. This is, I imagine you probably, question.
Just a quick thing. What does NP stand for?
That's, I think that's Latin, nota bene or something like that. It just means heads up, important note, I just started using it because it's convenient. Yeah. It's pretty standard though, I'm pretty sure. Yeah. All right. Okay, a couple other quick things to talk about. I assume that y'all have seen this formula before. If you need a unit vector pointing in the direction of a given vector, divide the vector by its own magnitude. Very handy. Not much needs to be said there. Easily seen to be true. Related also to dot products, this idea of a component. Component is something I'm going to motivate geometrically, and we'll write down some formulas. But suppose you've got a vector v. The vector v, non-zero, of course. That vector v defines a direction. Suppose that is the direction that we care about for whatever reason. And an easy example is we're playing football, and you need to know if you make a first down or not, and it doesn't matter how far you go left, right, it's all about how far you go forward. Right? Only the forward component matters. Okay, so given a vector, not necessarily in the direction that we care about, what we call the component is this distance here. It's if the ball was there and then there's a running play and the ball ends up there, the component says how many yards were gained on that run. Does that make sense? Okay. All right. So, we've got ourselves a little trig problem here, and not hard to see that, let's see here, let me get all this on the screen here, that this angle, theta, is going to play a role in that the cosine of that angle is the purple side divided by, the magnitude there, in other words, the hypotenuse, and that's the magnitude of W, that is the hypotenuse there. So purple over dark blue is the cosine of orange. Is that cool? And you write that down, and now just a little bit of, kind of moving things around. This turns into that. And handy move. This is a nice little slick trick. Let me clean up the picture. We notice that this expression looks an awful lot like the classic geometric formula for dot products. And so with that in mind, I'm going to do this. And again, this is just, algebraic trickery, but I'm going to multiply and divide by the magnitude of V. Perfectly legal. Right? Perfectly legal. Didn't do anything. But because of what had been there previously, that makes the numerator turn exactly into the dot product. So real slick little move, and thus our formula for how to compute components is right there. So there you go, good formula to memorize. Now here's an alternative version of this. I like this one a lot, and that is to notice that the unit vector that we just talked about, the unit vector in the direction of V, is right here looking at us. And so I think this is an even better formula then for components is that whatever, if you want to find the component of some vector W, just dot it with the direction unit vector. Components are dot products with unit vectors, which I think I wrote down here. Yeah, here we go. Components, let's see here, let me go back to blue. Components are dot products with unit vectors. So, in my mind, this is the formula. This is the formula I have memorized because it's pithy, right? It's easy. It rolls off the tongue nicely, right? It's another way to say it. This is a lovely feature of unit vectors specifically. So again, there's an idea in play. I don't do formulas. I do ideas, right? I see ideas in this formula. If I had to go off of the formula, I am convinced, knowing myself as I do, that I'd get the denominator wrong. I'd accidentally divide by the magnitude of W just because it's just a formula, and I know I'd get it wrong at some point. Yeah.
So just thinking through this formula,
Yep.
Where does the cosine of theta go?
Yeah, right. It went inside of the dot product. Yeah, it's still there. It's just hidden inside of a much easier to compute formula. Yeah. Is that cool? Yep. Everybody happy? All right, now here's a closely related idea, but different. Closely related, not the same. This is the idea of a projection. Now, a lot of the same picture. We have a vector that defines a direction. We already talked about the unit vector pointing in that direction. We've talked about having some other vector not pointing in that same direction, presumably, and wanting to know, well, yeah, but how far does it point in the relevant direction? And so there's our component there in orange. All of that's old news, already done. The related, new, different idea is to ask not what is this distance, but what is this vector that points in the direction by an amount, which is the component. Right? So let's make sure to distinguish between orange and purple here. Orange is a it's a scalar anyway. I'm going to sloppily say distance. It doesn't have to be positive, so it's not technically a distance, but you know what I mean. It's technically more like a coordinate or a scalar. But orange is a scalar, purple is a vector. Does everybody see the difference? Okay. So what we have in purple there, that is what we call the projection. And so how do we find the formula for the projection? So different points of view that you can take on this that are all reasonable, I suppose. But this purple vector we're interested in, I know two things about it. I know already what direction it points. Let's see here, color choices. It points in the same direction as the unit vector that I already have a formula for. I also know its magnitude. The magnitude of that purple vector is the component that I already have a formula for. So, boom, we're done. We didn't have to reinvent the wheel and do all that trig over again, whatever. I can just infer from what I already know what the formula has to be. Everybody good? Okay. All right, so again, we already had this formula here for component, dot product with the unit vector, and of course we already had a unit vector out there, and so grand total, there's your formula for projection. It's W dot U times U. All right, now the book takes a different point of view on this. It's what I would call, fine, I suppose. I'm going to complain about it though. Everybody's got their own point of view on things. I'm sure the author would complain about how I do things. So anyway, the author gives the formula that results from taking that U and this U and plugging in what those formulas for that U are, right? And then you move things around a little bit, and what you end up with is, instead of instead of this formula for projection, instead that formula for projection. Now, which of these do we like better? Pros and cons. Let me make the case first for the bottom formula. The bottom formula, it's very plug and chug, right? In the bottom formula, you're asked for a projection of a vector W and a direction V, and the answer is in terms of W and V explicitly. That's kind of nice. It's very plug. If your job is to plug and chug, you got to go with the blue formula. Okay, now that it was a backhanded compliment, right? I've already pointed out that's not our job to plug and chug into formulas, right? Our job is to understand ideas. I think the ideas are more evident and more sort of visible up here. Right here you can see where everything comes from. That defines my direction. That defines the magnitude. The formula above more readily connects to ideas that we can see geometrically. I can remember that formula because, again, I don't do formulas. I do ideas, right? I see the ideas in the orange formula. I remember the orange formula. I do not remember, and I don't trust myself to remember this formula down here in blue. So anyway, they're both true. I think the orange one is better for what I think the Math219's purposes are. Okay. All right. If I can get that to display. There we go. Okay. All righty. So real quick last comment, then we'll go on to the next chapter, or the next section. Again, tough choices, right? I wish I had triple the time that I have. I'm sure y'all don't wish that. But anyway, so I have to make these tough choices of what I can spend time on, what I can't. And there's a couple of nice examples in the book that allow you to prove certain facts of plane geometry that are harder if you just use kind of high school geometry techniques. But if you use vector algebra as a tool, it turns out these things are easier to show. So yet another reason that we like vector algebra. Give those examples a look. They're pretty straightforward. If you have any questions, of course, I hope it always goes without saying, come to office hours, answer any questions you want. But until then, give them a look, see if you can't work those out on your own. Yeah?
Do we need to know, projections onto higher dimensions?
Well, I notice that these formulas are independent of dimension here. Yeah, I kind of seemingly drew 2 dimensions, but there's nothing about the algebra in here that's intrinsic to 2 dimensions or 3.
I mean, to a plane or a 3D space.
We're going to eventually get to that. But for what I've described here, no, but we will. What you described, we will get to later. Yeah. Right. Okay. Okay, so I want to move on to section 1.4, and we're going to talk about the cross product eventually. So real quick, let me say a couple of words about how I'm going to approach this section. There are a bunch of ideas that connect to each other involving cross products and determinants and what I'm going to call geometric order of a list. And they all connect in these sort of different unexpected ways. When that happens, it's not immediately clear which one you should take as the starting point, and then what path you should use through the ideas to get it all done. It's kind of a traveling salesman problem, right? If you have let's suppose that you're a traveling salesman. That used to be a thing. I don't think it's a thing anymore. But if you had to, you got to go between 10 different cities, and you got to get to all the cities. It doesn't matter particularly which order you go in, other than you want to do it the order that requires the least amount of driving. How do you decide what the right order to go is between the cities? It's a surprisingly hard problem in general. So there's something kind of like that going on here. We've got a bunch of different ideas, and how do I most conveniently get sort of through all of them? There are persuasive cases to be made for many of these different approaches. I have my own approach that I think is what I'm going to call, I think it's the best for as effortlessly as possible getting as many ideas as possible that are as geometrically satisfying as possible. So there are downsides to the approach that I'm going to take. What I'm going to do is going to assume, or is going to not prove some things, and so be it. This is not Math 222. This is Math 219. So we're less proofy. We're more, results and intuition. So I think this is appropriate for Math 219. So that said, the approach, the order that we're going to cover topics in my presentation on this is going to be different from the order that the book uses. Okay, so just FYI. All right, so let me start off by talking about what I mean by geometric order of a list. First of all, what do I mean by a list? And list is going to be short in this section for ordered list. I will always mean ordered list when I say list. And if you think about it, most lists are, something's got to be written down first. Okay. All right, so for example, here's an ordered list, A comma B. There's two vectors in there. That's a list of vectors, but I emphasize it's an ordered list. A is first in the list. B is second in the list. That is part of what we mean by this as a list. This is not just two vectors A and B. This is A first, B second. Is that cool? Everybody see what I mean by the ordering? Okay. All right, now just to keep things simple, I'm going to represent that by an arrow showing that A is first, B is second. Okay. All right, so how would I describe this list? A first, B second. What can I say about it? And just as a dumb example, I would point out you could say, that list is in alphabetical order. Right? It's true. And useless and arbitrary, right? These vectors A and B, I could have called them Q and L, right? I mean, who cares about the labels that we've stuck on them? That's obviously meaningless, right? So I want to describe this list in meaningful geometric terms. And I propose that if you were to draw those vectors, and if they were to perhaps look like what I've got over here on the left, I think that should be called a counterclockwise list, if that's how those vectors fall. A first, B second, you're intrinsically, the process of going from A to B, that is intrinsically counterclockwise. On the other hand, let's suppose that the vectors were like this. That, again, still A first, B second. But if these are what those vectors actually are, notice that is clockwise. It's, all right. Now there's a collection of other cases that are all kind of annoying. The vectors could be pointing in the same direction, in which case it's neither clockwise nor counterclockwise. They could be pointing in exact opposite directions, in which case it's really neither clockwise nor... One of the vectors could be 0, the other vector could be 0. They could both be 0. There's various, other cases, and what I think is convenient to notice, all of those other cases, the vectors are linearly dependent. So I just lump them all together. The case 3, I like to call, is linearly dependent. I'm just going to usually say dependent. Is that cool? Okay, so now this is one way to do it, but furthermore, this idea, this geometric feature of the list has some nice properties. If I have this pair of vectors, correction, if I have this list, ordered list, A first, B second, notice that list is counterclockwise And if I were to take the reflection over a line of that counterclockwise list, notice what I get as a result would be clockwise. So loosely speaking, the way I'm going to say this is that clockwise and counterclockwise are mirror images of each other, or you could say they're reflections of each other. There's probably other choices of words that would be satisfying. Everybody see what I mean by saying mirror images of each other here? Okay, so how about that? That's pretty cool. So this geometric choice that we've made has a natural and simple geometric property. So this is not arbitrary. Something cool has happened here, right? This is a geometric feature that behaves predictably in certain ways. Okay. Here's another cool feature. If you change the order, that changes the geometric feature. So, A first, B second is counterclockwise. Now, notice if I take the same vectors, A is still the same vector, B is still the same vector, right? I'm not changing the vectors at all. But if I change the order that I write them down, where B is first and then A is second, notice that changes counterclockwise to clockwise. Now, you could say that's a silly observation. Of course it is. You're just literally saying go backwards. Okay. But still, this algebraic process of changing the order in the list has the geometric consequence of turning clockwise into counterclockwise and vice versa. So it may be obvious, but it's meaningful. Okay. And let's see here. The order is independent of rotations. So if you have, for example, this list AB, notice that is counterclockwise. Okay, now if I were to take this whole picture, that whole picture, just rotate the whole thing. I'm going to rotate A by some amount. I'm going to rotate B by just the whole thing. Just rotate the whole thing by some amount, theta, right? Whatever. Having done that, notice that the new list still counterclockwise. So this is when I say independent of rotations, what I mean by independent of rotations is that rotating doesn't do anything to clockwise versus counterclockwise. Here's one way to think about it. If you look at a clock face, like a regular clock face, with the hands going like that, right? If you turn your head to the side, it still goes the same direction, right? So, of course it does. Again, silly, obvious observation. All right. Okay. So, now that's two-dimensional. Now I want to talk about in 3 dimensions. Here's where things get tricky. Here's where things get not obvious. What if instead of having 2 vectors in R2, what if you have 3 vectors, an ordered list of 3 vectors in R3? So now we're talking about vectors in space. And I've got 3 of them instead of 2 of them. I mean, that's not how clocks work, right? I can't just say clockwise, counterclockwise. This becomes a much less intuitive situation. Right? So there's a nice way to do a shockingly similar thing, though. That's what we call right-handed and left-handed order. I'm going to have to do a visual, physical demo. Sorry for people watching the recording. It won't come out on the recording, of course. So there's a convention for how to do a certain hand gesture that will arbitrate whether your list is in what we call right-handed order or left-handed order. I'm going to show you right-handed order first. So I'm going to use, not surprisingly, my right hand. It's got to be a human right hand, no aliens. Okay. Index finger. Point your index finger so that it is parallel to your palm. Right. Now, with your middle finger, bend your middle finger in the direction that middle fingers want to bend. So no funny business, like this. Right. So index finger parallel to the palm, middle finger bending the way middle fingers want to bend. Having done that, now you can go to your list of vectors. Let me just come over here, and you'll notice that the way I have my hand pointed right now, these fingers are not pointing in the direction of any of those, but if I arrange myself carefully, I can point my index finger in the direction of the first vector there, A, and then by twisting my hand appropriately, I can get my middle finger in the direction of B. And notice I'm still following the rules. Index finger in the parallel to the palm, middle finger bending the way middle fingers want to bend. All right. When you do that, A and B, index finger, middle finger, define a plane. Your thumb points on again, no hand yoga, right? Thumb's doing what thumbs want to do. Your thumb points on a well-defined side of that plane. If the third vector, C, is on the same side of the plane as your thumb, then we say that is a right-handed order. Left-handed order, you can probably guess, right? So I claim this is a left-handed order because index finger, middle finger, thumb. But try as I might, I cannot make, for example, this right-handed order. It's not going to work. Let's try, just for the humor value, if nothing else. A in the direction of the first vector, index finger in the direction of the first vector A, fine. Now, can I get my middle finger to point in the direction of B without doing the, again, cheating, stretching your middle? Well, yeah, sure, just do this move. Now my middle finger is in the direction of B. Notice my thumb is pointing on the wrong side of the plane. My thumb is pointing down. The third vector C is pointing up. We lose. Right? So unavoidably, this, as I've got it drawn here, is just only works with left hands. And this that I've got here only works with right hands. Does that make sense to everybody? All right. Okay, again, there's various different sort of exceptional cases, all of which, again, are linearly dependent. I don't want to enumerate all the possibilities, but it's all the different versions of linearly dependent. Right, yes?
Just a question with right-handed and left-handed.
Yeah.
The way you draw them makes them look like they're all orthogonal to each other.
No, they don't have to be orthogonal. And you could make the case that this looks orthogonal, but it doesn't have to be. And a case could be made that I didn't indicate that it was orthogonal. So yeah, right, yeah.
So like when you're doing the rule, you just want to when you're seeing them and they might not be
Yeah. So notice the angle that you make with your middle finger could be like this. And that's fine, as long as the middle finger is bending the way it's supposed to, right? As long as it's not going backwards, then it doesn't have to be. It could be less than a right angle. It could be more than a right angle, also fine. Yeah. Cool. Okay, so the sort of three-dimensional version of clockwise, counterclockwise, right-handed, left-handed. And here's a beautiful fact. It's got a lot of the same properties. Right hands and left hands are mirror images of each other, right? I don't know if you ever thought about that. But right hands and left hands are always mirror images of each other. Just like with clockwise, counterclockwise. If you trade the position of two of the vectors in the list, it changes the order. Just like clockwise, counterclockwise. Maybe a little bit less obviously so. But still, same fact. Trading two positions changes the geometry. Now let's walk through. I just want to make sure we interpret all this correctly. So why is this a right-hand order? Let's think it through. Okay, A first, B is second, C is third. Cool, right-hand order. Right? But now I also claim that BAC is a left-hand order. Now, again, keep in mind, now, that's the ordering I'm talking about. B is first. Right? Forget about alphabetical order. It's not about alphabetical order. So B is first in that list. So index finger B. Second is A, middle finger in the direction of A. C in the direction of the thumb. So sure enough, this is a left-hand order. Is that cool? Question?
So since there are 3 vectors, if you change it so that none of them are in their original positions, would that be basically like not changing the order at
Yeah,
all?
you mean like if you put A where B was, B where C was, and C where A was?
I think so, yeah.
Yeah.
It would just be your right hand still?
Yeah, that's a great question. It's a nice insight, and I'm going to get to that in like 30 seconds. Yeah, that's a very, very good observation. Yeah, but so let me defer my answer until we get there. Okay, and then the last observation I'm going to make is that if you take, for example, any list so here we have a list A, B, C. That list is in right-hand order. If you take that whole picture and rotate, now keep in mind we're in 3 dimensions, so it's not just rotating around just in one direction. You could rotate in any direction, right? Rotate around any axis. Whatever you do, if you have a right-hand order, however you might rotate, still a right-hand order. Does that make sense? So notice we've got here the exact same 3 properties that we did for clockwise, counterclockwise. Mirror images, trading changes the order, independent of rotations. Mirror images, trading changes the order, independent of rotations. Now, the fourth one is exactly what you were asking, and this is what I like to call cycling the list. So cycling the list means that like per my response, you see that what had been third is going to the second position. What had been second goes to the first position, and what had been first goes back over around to the third position. So everything's kind of, everything moves and then it whips back around to the other side. And so there isn't really a 2-dimensional version of this quite. But anyway, nice punchline is that cycling a list of 3 vectors preserves the order. And the proof of this fact is another hand wave. Give me 2 seconds. It's another hand wave. Here, let's see. Okay, so, so here we go. There's ABC. And let's see here now. Let me do BCA. So, I'm gonna hurt myself here. Okay, ABC. Okay, so BCA. So notice I can still do it with my right hand. Right? I've just, what was second is first, what was third is second, etc. So cycling doesn't change the order at all. Yeah, you had another.
Well, so even if it's not like a perfect cycle, or maybe it is always a perfect cycle, it is basically trading positions twice, right?
Yep, it is.
So you're just going back
Yep.
to your...
Well, so it turns out that there's really only so many different ways that you can shuffle a deck of 3 cards, right? And the options are basically that you can leave it the same, you can trade 2 of the positions, or you can cycle. That's it. There is no hypothetical 4th case that I think maybe you were thinking. Does that make sense? Mm-hmm. Yeah. Yes.
Can you tell the order of 2 vectors in 3 space?
That's not really, because it depends on your point of view, right? So, for example, let's see my finger here. Is my finger rotating clockwise or counterclockwise? Exactly. Because from your perspective, it looks counterclockwise. From my perspective, it looks clockwise. So there isn't really an intrinsic answer. Right?
Is there like an algebraic answer at all?
I mean, but you can't answer a question where there is no answer, right? So that's the point there. Is that there is no meaningful, there is no unique canonical perspective on that. So anything you do with algebra would just be chasing what's the metaphor? Wild goose chase. Yeah, right. Yeah. Okay. All right. Let's see here. We've got 24 seconds. I don't think we're going to have time to get anything done. Let's just go ahead and draw the line right there. And we will pick up here on Friday, tomorrow. Okay. Good to see y'all again. See you on Friday. Don't forget office hours in my office in 15 minutes if you have any questions about either what we talked about today or the homework exercises that I hope y'all all attempted all of yesterday afternoon and evening. I'll see y'all tomorrow. Have a good one.